All right, this problem would have us put each of these three rows in order of acid strength. So we'll work on row one, row two, and row three separately. And basically what it's doing is it's kind of harkening us back to our acid base chapter, well back in the early days of Orgo 1, and it's just reminding us of the factors that affect acid strength. So in the first row, we have acidic hydrogen there, and there. Now this is the alcohol chapter, so we're going to be looking at OH groups for all of these problems. And clearly what we've got going on here is induction, right? And so there's going to be some induction for all of these with some electronegative atoms. And the more electronegative atoms there are, the more inductive effects there are, the more of that those inductive effects make the acid a little bit stronger. So this would be, if I were to say A, B, and C, then the order would be C is the weakest, B is next, and then A. Because look, we just got additional chlorines providing more of an inductive effect. Okay, what about this one? How are we able to consider the relative acid strengths here? Now, I have essentially the same OH groups as before, but instead I've got some additional branching. The only difference is the branching that's going on. So how do I think about that branching as affecting the acid strength? Well, this is going to be one of those times when we think about the solvent and the effect that the solvent would have on stabilizing the conjugate bases. We should know at this point that the additional branching creates steric hindrance that prevents the solvent from getting closer to the alkoxide ion that's created when each of these hydrogens are donated as acids. So I end up with these negatively charged oxygens, and one of the things that can stabilize a negative charge is if the solvent is allowed to interact with it. But because of the bulky groups providing hindrance for the solvent to get closer to that alkoxide, that O minus, that's going to make those acids a little bit weaker. So in this case, what's the strongest acid? The strongest acid here is C. And then the next strongest would be B, and the next strongest would be A. So the order is A, B, and C in this case, opposite as it was before. All right, what's going on here in the last row for A, B, and C? Well, we're looking at these hydrogens, and what we have going on here is the difference between resonance and no resonance. Now, we should be able to tell at this point in our organic chemistry career that there's no resonance at all with A, and so it's going to be the weakest acid. But what about B and C? We have seen phenol and how the alkoxide of a benzene ring, or how the negative charge of a phenol counter a phenol. Let me try to say this one more time. The conjugate base of phenol, how that interacts with the ring structures in the benzene in order to show some delocalization of that negative charge. How does this work with B though? Is the nitro group helping or is it hindering? And so let's see if there's additional resonance. I think that if I were to say, let's at least be sure that we can convince ourselves that at the very least, it has all of the same resonance opportunities that the phenol has. So I can still show the negative charge delocalizing all around the ring. But what about the nitro group? If instead of on the carbon, can this resonate this way? It turns out it can, right? So you see that that negative charge can delocalize all the way out to those other oxygens. So there's even additional resonance contributions to B that serves to stabilize the conjugate base. So A is the weakest, then C, then B in this case. Okay.